Give me a moment here. Somehow I cannot share my screen. Okay. All right, we're on. All right. Do you have any questions, Dion? Okay, cool. Awesome. So let's see here. So last time, we were discussing the Merton's structural model. Credit model. So basically, this is a very cool application, okay, of the Black-Scholes model, and of course the Black-Scholes formula as well, to estimate a company's risk of default. Okay, so you wouldn't think, right, when a company issues like that stock and stuff like that, there would be subject to risk of default, but there is. Okay, and actually the default is connected to the debt. Okay, and so the Merton's application. So the model is nothing new, but the application of the Black-Scholes model to this situation reveals many things that we wouldn't normally think of in terms of the usual option pricing. So the context again is like this, right? A company has asset, okay, at time t, denoted by AT, okay, and this asset includes everything from the company's properties to its cash to whatever, like cars, whatever it is that it owns, and we consider this asset under the risk neutral framework to have the following return, right? DAT over AT, if you will, right? Under the risk neutral, right? I'll put A here. Under the risk neutral model, then the rate of return of asset will be risk-free, just like anything else. Okay. And so sigma A, right, is the volatility of the asset. Okay. And pay attention, the asset is not the stock price. Okay. The asset is not the stock price, or the asset is not the firm's equity. Okay. We will get that in later. So the firm also has debt, okay, has a debt. And the debt, to make it simple, let's suppose that it has a debt at level D, okay, to be repaid at time T. So this is like a corporate bond, okay? This is a corporate, it's like a corporate bond with face value big D, like $1 million, $10 million, whatever, right? A company issues a bond, right, to be paid back at time T, big T. So again, right, it doesn't have to be one single bond, but like could be 1,000 bonds, for example, but the total value is big D. Okay, so the equity level, right, the equity, which basically is what the company stockholder is entitled to, is not the company's asset, right? But it's going to be the company's asset. Here's at time big T, right? It's a company asset after you take into account the debt. So in other words, the equity will be whatever is left over if you have, sorry, big T, right? Because you have to pay back the debt, big T. It will be whatever that's left over if you have more asset than debt. But if you have less asset than debt, then all those assets must be used to pay the debt. So in other words, you have no equity if you have less asset than the debt level. In other words, the equity level at time big T is nothing but a co-option on the asset of the company with strike level D. Okay, so that's Merton's insight, that the equity, right, the company's equity is a co-option on the company's asset with strike big D. Okay, with the strike being the debt level. So that means that we can compute everything. For example, we can compute, right, by Black-Scholes formula, because we assume that the company's asset return follows a Black-Scholes model, that the equity level at time zero, right, will be asset level at time zero, and the plus minus, right, debt level, e to the minus RT, and d minus, where d plus minus is r plus minus 1/2 sigma square sigma asset, right, times t minus the natural log of debt over the original asset level divided by volatility of the asset square root of t. Okay, just like Black-Scholes. But this is not necessarily what we're interested in right now, because, right, the equity, for one reason, I mean, equity is directly tied to the stock price. So you can observe E, right? E in general, ET, the equity level, through the company's stock price. One estimate would be you take the stock price, you multiply with the total share outstanding, right? How many shares they have issued, multiply with the price of share currently, you get the equity level, okay? So that's not something earth-shattering where we apply this formula. Actually, right, this formula gives us access to something that we don't observe on the market directly. For example, right, notice that throughout all this model, AT is never directly observable. Okay, you don't have a look into the company's like account book to know how much land they own, how much cars they have, that kind of thing, right? How many cars they have, that kind of thing. So how many office space they have. So in that sense, right, this is a classic formula or a classic situation of using, right, something you observed and then deduce back on something you don't know, okay? Namely the asset level, but that's not what we're interested in, like purely, but what we're interested in, first of all, right, is the risk of default. In other words, let's say you're an equity holder, and actually if you're a bond holder too, right, you're much interested in the probability that the company goes default In other words, the probability the company cannot pay back the debt. What is that, right? So risk of default. There are many risks of default that we will talk about in this particular example. But one possible risk of default, right, is the probability that the company end up having less asset than the debt level. Okay, let's do this too, right? Because if the asset just barely hit the debt level, we also consider that to be default. Anyway, that will be 1 minus the probability, right? AT bigger than D. And we discussed how ND minus, right, is a probability that the stock ends up in the money. So it's exactly 1 minus ND minus, or that would be N of minus D minus, because by the symmetry of the normal distribution. Okay. So that's where we ended last time. Any question here? Now, so several things. First of all, what I wrote here is not exactly precise. The number one thing that stands out is that this is not a physical probability, but is a risk neutral probability. Okay. In other words, right, because we assume or we use the risk neutral framework to price the asset, right? To price the equity, right? To price the equity. What that means is we automatically in a framework that is not the physical world. So you could make the argument that, well, it's all fine and good, except that I don't believe this, because in real life, right, my company is very different. It doesn't have rate of return R. So potential issue, right? P tilde is risk neutral, right? And we live in the physical world. All right. So this is a valid issue, and the way that people modify this, or the way people use it, is like this. Well, so a particular value of P, like the risk of default here, may not tell you much. But on the other hand, right, a high probability, even in the risk neutral world, should give you some concern. Like suppose somehow you calculate this and you got it to be 90%, there's something going on there, all right, to begin with. But to be more precise, even though, right, we cannot take a number from here and say that the company has 50% chance of defaulting in the real world, what we can do is we can compare, right? The P tilde has a relative value, relative comparison value. Okay. In other words, suppose we have two companies, company A and B. Okay. I'm going to run into trouble here because I use A and B already. Let's say company 1 and 2. Okay. So suppose that you compute this and you saw that the probability of the company 1, right, being defaulting is higher than the probability of company 2 defaulting. Okay. So notice, right, the debt level of these companies could be different. They're different companies, they have different debt, different asset, right, at the end. But if I compute this and I saw that the risk of default, right, risk neutral, is higher for company 1 and company 2, you could sensibly infer that the same thing holds in real world. In other words, in the real world, this should be the same too. Okay, so it should hold. Of course, no one say that this must hold, or that's not like a rigorous argument that lead you to say that what happens in the risk neutral world must hold in the real world. But at least that's a reasonable thing to say. So in other words, what we can say is, right, that if we cannot know specifically about the risk of default of one company, but if you have like 10 companies together, okay, then you can compare the risk of default of each of these companies with each other using this framework. And then you can come up with a ranking of the most the riskiest company in the list to the least risky company in the list on the list, okay, using this scheme. So that's the value here. It gives you a way to rank the companies in terms of their riskiness of default. Questions? The second issue with this calculation is this, and this will be an issue throughout Merton's framework. So pay attention to the way we calculate E0 and the way we calculate D plus minus. What do we need, right? We need A0, we need sigma A, right? D and T. So observe that here, right, that a company's debt level is public, right? How much bond they borrow, that they must disclose that. You can see it, okay? The time of the debt, sure, right? How when the bond matures, that's public information. Of course, the risk-free rate is public information. The company's initial asset level is not public information. They don't have to disclose it. The company's asset level volatility is also not public information because you don't observe, right, the trend of the company's asset in real life. You observe the equity, right, how it moves by the stock, but you don't observe how the asset move, right? You don't know if the company has decreased or increased in asset in general. So the second potential issue is the, again, right, non-observability of A0 and sigma A, okay? So even though, right, we make a big deal of, yeah, right, if we could calculate this guy, then we're good. At least we can compare different companies' risk of default with one another. But then immediately we see that this is not directly calculable because no one will tell you, right, what a company's asset level is and its volatility, the volatility of the asset. So how do we get around this issue, right? Otherwise, the formula is useless. It's theoretical, but it's not, practical. So the way we get around it is like this, and this is a little bit, subtle and tricky, but stay with me on this, okay? So first of all, do take into account what we can observe. Again, right, we do observe E0, okay, the company's initial equity, and sigma E, the volatility of the equity, okay? And this is again through stock price, through the company's stock price, okay? And you see why here I distinguish sigma A with sigma E, right? There's not only one sigma, there's not only one volatility. There are two volatilities going on. One is a volatility of the company's asset, and one is a volatility of the company's equity, okay? One I'm interested in, but I don't observe directly. One I'm not super interested in, but I can observe directly, okay? So the key is somehow to deduce, okay, A0 sigma A from E0 sigma E. And notice that actually if you could do this, then already the Merton's model is of much value to you already. Why? Because again, right, you agree that a company's equity level and its volatility does not tell you exactly the whole story. because it depends on how the companies get into its debt and its debt structure, right? Um, that that does not get reflected directly from the equity story. So, but if you can deduce from back from the equity story into the company's asset, then your judgment may be much more right precise. So anyway, right, how do we do this? The story here is basically the story of you have two unknowns, right? In other words, the initial asset level and the volatility of the asset. So you need two equations to solve for these two unknowns. So where do we come up with these two equations? The first equation actually is the pricing equation, because this equation, right, ties the equity with the asset. So in other words, the first equation is just the good old pricing Black-Scholes equation. Okay. What about the second equation? The second equation is where things get a little bit subtle. All right, so stay with me here, and it will have connection with what we'll discuss later, namely the Black-Scholes PDE and the Greeks. Okay. What we do is like this. What we do is we do some kind of Ito formula extension on the equity near time zero. Okay. And here's the formula, and I'll explain. The formula says this: the equity, right? So delta t is something small, close to zero. Okay, just a split second after. So this will be the change of the equity with respect to time times how long time has elapsed. The change of the equity with respect to the asset times how much the asset has changed. And then the second derivative of the equity with respect to asset. And then here times this quantity. Okay. Now, if you notice, this is just Ito's formula part 3 that we talked about, where, remember I said, if you have a function f of t xt, then df is going to be f sub t dt plus f sub x dx plus 1/2 f sub xx, the quadratic variation. That's exactly what's going on here, okay? Where f is the equity and x here is the asset level. Even more importantly, I mean, if you want, we're going to go to the next the topic of the Greeks very soon. The Greek are the measures of how sensitive the option with respect to the underlying. So here, this quantity is called a theta in the Greek, and this quantity is called the delta in the Greek. Okay, and this is called a gamma. So if you want, and if you do come from a finance background, then you can look at this as the expansion or the approximation of the change in equity in terms of the Greeks. Okay, this guy. Either way, right, it doesn't affect what I'm gonna say next, which is if I compare this and this, okay, what I'm interested in is to relate. So by the way, delta A here is A at delta t minus A0. This is the change in the asset during that time. So I want to relate this and this together, okay? And the best way to do that is to take the standard deviation on both sides. Okay. What I mean is this, and I'll show you. So for example, right, when you look at the model, right, for the equity price, right here. Oh, sorry. Let's say the asset, right here, right. What this says is this, that the change in the asset, right, is the asset level times the interest rate dt plus the asset level times the volatility dw tilde t. So if you take the standard deviation right here, what you end up is this term doesn't add to the standard deviation because that's just a constant term. What you end up having is this term right here contributing to a standard deviation of the change in asset level. How much contribution exactly? It will be AT times sigma A times square root of delta T. Okay, why so? Because sigma A, right, is right here, AT is right here. The Brownian motion, right, a change in the Brownian motion is variance is delta T. So its standard deviation is square root of delta T. All right. So same thing here, where I have the standard deviation of the equity, almost by definition, will be its volatility times its initial value times square root of delta T. Okay. Or, okay, I have a better way to explain this to you. That what is volatility, right? What is volatility? So we use this term a lot, but we did not give it, right, a precise definition. Volatility basically is standard deviation, okay, SD for standard deviation of returns per unit of time. Okay, that's volatility. So in that sense, right, what is return per unit of time? Well, return, right, is this. This is percentage return. So if you take the standard deviation of this, and standardize by the unit unit of time, then you got the volatility. And so exactly that's why I claim right here. Okay, because E0 is the volatility at the beginning. Is the equity level at the beginning, so it's known, it's a constant. You can multiply it over here. Also, you multiply this over here, and you get this. All right. So that's this guy. The standard deviation on this side ignores these two terms because they don't contribute to volatility. They contribute to the average. So this term right here, right, contributes to the volatility. So in other words, the standard deviation of the delta, all right, this is the delta of the equity with respect to the asset times AT minus A0, okay, will be, so the delta is like a number. It's a sensitive change. It can go out. So it will be this times the standard deviation of the change. Well, guess what? This will be exactly like this, okay, or like this, but with the asset instead. So it will be the delta times A0 sigma A square root delta T. Okay. So in other words, we got a very beautiful equation at the end of the day, connecting these two. And actually, for making a big deal out of this thing, right? At the end, what we got is like this. The volatility of the equity times its initial level times how much time has passed is equal to the delta, or the sensitivity of the equity with respect to asset times the initial asset level times the volatility of the asset times square of delta T. Or, right, you see these two terms don't matter. You can cancel them. You got this. And I think this makes a lot of sense. This is just kind of saying that, you know, the volatility of the two respective, right, you know, entities are connected by their sensitivity. Okay. All right. So this is our equation B. Don't forget the story. The story is that we want to relate the asset, or we want to deduce the asset from the equity. So we need two equations, right, to solve for these two unknowns. The first equation is a pricing equation. The second equation is right here, and you can call it the delta equation or the sensitivity equation, okay? Now, what is this strange guy, right? What is this guy? How do you compute it? You compute directly from the Black-Scholes model, actually, Black-Scholes formula, actually. You compute it directly from here. And we will discuss it, you know, more at length when we discuss the Greeks. For now, just trust me that this guy is exactly ND plus. So the delta of a call option is ND plus, okay? The sensitivity of a call option with respect to the underlying is ND plus, where the ND plus is the, you know, in the Black-Scholes formula. So again, right, remind you that the ND plus here is R plus 1/2 sigma square T minus log of D over A, okay? Don't forget that this is the D in terms of A. So sorry, sigma A here, okay, like that. All right. Any question here? Okay, so I want to say one thing, right? So as from the theoretical point of view, when we have these two equations, we're good, right? There's nothing else we need to say. But from a practical point of view, no one will be able to solve these two equations by hand because these two equations are highly nonlinear, all right? So if you ever want to attempt to solve these two equations together, then you need some kind of, you know, package, numerical package from MATLAB or Python or something, or you need to build your own numerical method, okay, to solve this. And that's where, like, you know, the side of the field of math called numerical analysis becomes relevant, because when most of the time in complicated models, any equation you come up with will be highly nonlinear. So the chance you solving it by hand is none, almost none. So you have to use, right, sophisticated, well, not maybe, you have to use more advanced techniques in the numerical algorithm to solve it. Okay, so I have addressed these two issues of the, you know, computing, right, the risk of default for Merton's model. Any question? Okay. So the next one is another way to look at this this default. So we look at the default in Merton's model by pricing of the corporate bond. Okay. So what is the corporate bond in Merton's model? The corporate bond, right? Let us denote BTT, okay, to be the price of the bond. Issued by the company at time T. Issued by the company, right? Sorry. By this company that we just described so far. And then we want to say with expiration, right? Big T. So here, right, exactly, this is the debt that we were discussing. What's the value of the debt? So here, right, this is a very conventional way to denote the bond. The second entry tells you the expiration. The first entry tells you what time you're looking at in terms of the price. So let's address one thing right away, that BTT, right, which is the value of this bond at time big T, right, is it equal to D, the debt level? Well, the answer is no, right? Exactly, the point is that the bond price is not equal to that level. Because if it is, then it's just going to be a regular non-defaultable bond whose price will be discounted, right? E to minus RT times D, right? The whole point is that here the bond can be defaulted, right? This is a defaultable bond. Exactly by the story that we have been describing so far. In other words, the bond holder at time T will be receiving this amount. Okay. Why is that so? Well, what does this say? This says that, right, if the asset level is higher than the debt, then they get the debt back, right? Which is true. If the asset level is lower than the debt, then they cannot get the debt back. And they only get whatever asset, right, that a company has left. They take all the company's asset, but they will not be able to recover their debt level, right? So the point is, right, you see this is exactly no higher than D. And it has a positive chance of not being equal to D, okay? So when we price, right, when we price this bond, we must be sensitive to this final value, this terminal value. It's not a constant D. It's this stochastic quantity, all right? So, well, what does this mean then? What this means is we can translate this, right, into the language of the put option in this way. Is D minus D minus AT plus. Okay. So again, right, try to see why this is true. What is D minus AT plus, right? D minus AT plus is going to be 0 if AT is bigger than D. And it's going to be, right, D minus ET if AT is less than D. Well, is it consistent with the story we've been telling so far? Yeah. So if we have more asset than debt, then you see this is zero, then you receive the debt. If you have less asset than debt, then this will be this, and if you subtract this 2, you get exactly 80. Again, right? Same as what we've been telling so far. So this and this expression are equivalent mathematically. But put in this way, right, what do you see? You see that, right? So just as the insight that a company's equity, right, is a call option on its asset, the company's debt, right, or the company's bond is, like holding a non-defaultable bond, right? With face value D, right? With same face value. That's the D part. It's non-defaultable because that's a constant D, so it's non-defaultable. But then, of course, you also N shorting, right? A call a put option on the company's asset with strike level D. Okay. So it's a complicated way to say this, but that's what it is, right? So the defaultable bond can be decomposed into two components, the non-defaultable portion, which is D, and then the put option. Okay, but it's a minus, so you're shorting a put option on the company's asset. Any question here? Okay, so then you can price, right? You can price the price of the bond, let's say at time 0. Okay, to be, so first you discount this, right? Which is just D e to minus RT. And then you subtract the price of the put option, which you've seen on the quiz. In this case, it will be D e to minus RT and D minus. Sorry, there's a minus D minus. And then minus, right, the strike, which is, sorry, minus the asset, which is A0, and minus D plus. Okay, so this is, right, Black-Scholes price for put option that you have done on your quiz. Well, these two quantities can be combined. And so all in all, what you get is this. Sorry, A0. Any question? So as usual, all right, what the value of something like this does not lie in the direct pricing formula, but the value lies in some indirect quantity we can get from reading off this formula. For example, okay, the one thing that is true but is not easily observable is this, that the bond price here is no more than this, and it should be strictly less. Okay. So why is that so? That is because, right, what is this? This is the price of a non-defaultable bond, right? It's this guy right here. Okay. And then this is the price of the put option, which you know is always non-negative. So when you subtract the two, right, this will be less than that. And right, it should be strictly positive. So it should be strictly less than. So again, right, the inequality right here, this put option is exactly the price of the default. In other words, right, the bondholder do not want to pay the full price for the bond because there's a chance they will not recover the debt. So you must subtract, or you must discount, right, exactly a portion that covers them for in the case of the chance, right, in the case that the loss happens. And that loss, that is exactly, right, reflected via the put option portion, or, right, right here with this observation. Okay. So the second thing is when it comes to bond, okay, people don't really look at bond price, okay? People don't really look at bond price. The reason is, there are probably several reasons, but one reason is, bond price doesn't tell you much because it's inflated by the face value, right? If you buy a bond of $100 million, then the bond price is super high, like, I don't know, 99 million point something, something, something. But the point is this, right? That when you buy bond, when you're into the bond market, what you're interested in is the rate of return, okay, or the yield, right? So the quantity that people you should pay attention to is something called the yield to maturity, okay, of the bond. Which by definition is going to be the quantity, right, for a bond. Its yield to maturity is y, okay, let me do it small y. Is a quantity so that when you discount and multiply with the debt, then you get back the bond price. Okay, so this is like good old discount, right? But of course, this is debt level. So this guy right here is meant to capture any risk of default that may be built in the face value. Okay, in other words, if there's a default where you won't recover the debt value, then this guy must be higher to compensate you for that. Okay, so in other words, here's this. If, right, the bond is non-defaultable, which, by the way, right, is like a government bond, like the US bond is non-defaultable because you always think that the government can always print money to pay off the debt. So then the yield to maturity is exactly the risk-free rate. Okay, and actually risk-free, right, exactly refers to the fact that it's non-defaultable, risk-free. Okay, but here, right, exactly because our corporate bond is defaultable, so the yield to maturity for our corporate bond the yield to maturity should be strictly bigger than R. So that's another measure of risk for the merchant model. Okay, you can look at a company's bond and look at its yield to maturity, which is very easy to calculate. All of these are public information. And then you look at how far is above the risk-free rate. Obviously, the higher it is from the risk-free rate, the more, right, risky the company is. And finally, right, this quantity right here called the spread, which basically is on the yield spread, which is the difference between the yield to maturity and the risk-free, right? I mean, any yield to maturity, right, must be no less than the risk-free, because the lowest it can be is risk-free. So when you subtract this, this is a positive quantity, right? The higher it is, the more risky is the company. Okay. And the point of this deduction is this, that I think a company's corporate bond is actively traded on the market, I believe. So for that matter, right, this pricing equation has the added benefit that you could look up the company's corporate bond price right now on the market. So for that matter, you could deduce the yield to maturity, the spread, all this kind of good stuff. Or actually, you know, some source will quote you directly. Let's say the spread of a bond issued by Microsoft or something like that. So what that means to us is this, that again, right, notice this pricing equation directly invokes D plus, D minus, and A0, which are something we don't know. But again, if the bond price or equivalently the yield to maturity is known in the market publicly, then you can use that information, plug that back into this pricing equation, and deduce your own information in terms of the company's asset level and its the volatility of the asset. Okay. Any question on this? All right. So that finishes the Merton's structural model, which is, again, an application of the Black-Scholes pricing formula. Okay. So next, what I want to talk about is the Greeks. Okay. So the Greeks basically are the measure of sensitivity of an option with the underlying parameters. Okay. So what do we mean specifically by this? Let's just take a routine call option. So we have a call option, okay? And we know that the price of the call option, V0, is S0 ND plus minus K either minus RT ND minus. Okay. So how many parameters underlie this formula? So the parameters underlying this, whole formula is the following: the interest rate, the time to expiration, the strike, the volatility, and even the current stock price. Okay, so these 5 parameters. Now, traditionally, K is not really, a point of consideration, but these 4, okay, are the ones that we're interested in. What do we mean by this? For example, right? So a very, very, very easy question, and actually any trader holding any portfolio of option will ask this question. If the stock price moves a little bit, let's say up by 1 cent, how much do I expect my call option to move? Okay. And you can see that very similar questions can be asked on any of these parameters. Well, the T we'll talk about, right? But basically, it's this, that, for example, let's say if the interest rate, right, suppose the Fed made some announcement, if interest rate moves, it decreases, how does that affect your call option? The market just recently got more volatile. The volatility of the market increased, so which of course affects the underlying, right, the stock, the current company. Let's say somehow their volatility increase. How does that affect your call option? The T actually moves in a more interesting way, right? It's not really the T, the time to expiration that changes, because that's a constant. What changes is the time to expiration, okay? Because, right, as days goes by, your time to maturity, right, the time to maturity will decrease, right, will only decrease. So what you're interested in is how, as time moves on, the time factor, how does, as time to maturity gets shorter, how does that affect your volatility again, right? So the sensitivity that we're discussing exactly are referred to as the Greeks. In particular, right, this one right here in this question is captured by the delta. If we know the delta, right, of the call option, the delta, the notation is this, right, will be, by definition, the derivative of the call option, or whatever it is. It doesn't have to be call option, but just the option in hand with respect to the current stock price. Okay, if we know this, then the change, right, you see, then the change in V0 will be the delta times the change, sorry, in the stock, approximately, which approximately is delta times 1 cent, which is 0.01, whatever that is. Okay, so here, right, this is the change in call option price, and this is change in stock price. Is that okay? And well, for one thing, right, that we do not need to go super deep into these things, because the Greeks, right? So let me list out the Greeks. So you have the delta, which is the derivative with respect to the stock. You have the gamma, which is the second derivative with respect to the stock. You have the vega, which is the derivative with respect to volatility, right? This is called vega. This is delta. This is gamma. And then you have rho, which is the sensitivity with respect to interest rate. And then finally, you have theta, which is the sensitivity with respect to time to maturity, but with a minus, okay? And you understand why. The last one with a minus, because time to maturity always decreases. So you want to do a minus, so you kind of have that in perspective because it always decreases. Okay, because when we measure change, we always think of if this changed in a positive unit, how much does that change? So this is because it always decreasing. Okay. So these are their symbol. I mean, they might be written in a slightly different ways. The point is this, that frankly speaking, you can look them up on Wikipedia. Okay. I mean, all these are listed and more. Like there's the Vollmer and all those other exotic stuff, like the partial, the mixed partial. What I'm interested in, right, in discussing here are two things. First, how to calculate, right, some of these things, especially the delta, and let's say the gamma, right? How to calculate, right? So the goal is to show how the calculation is done. And B, right, interpret the meaning of the Greeks in terms of auction price. Okay. So it's not just that you should know the formula and that's it and you leave it. The whole point is, right, especially with the people who deal with options day in, day out, they look at the Greeks not as numbers, but as signs, as meaning. Okay. When they look at a number, they immediately know, for example, this means this means this, this means that the price will react in a certain ways. Okay. So we want to at least put some, meaning on these things. So for example, let me give you something very simple in terms of item B. That the vega, okay, which is the sensitivity of the option price with respect to volatility, are positive, okay, is always positive with respect to for both call and put option. Okay. So A, this is a very interesting fact mathematically. We want to see that this is true. Okay. By calculation, of course. But because I don't know if you may just out of intuition, you may think that call and put react in opposite manners, right? So if something is positive for call, you would think that is negative for put, right? So those kind of, I don't know, hasty thinking, right, is something we want to kind of correct on. But so first, the vega is always positive for both call and put. But second, what's the meaning? The meaning is this, that's very simple, and it's a message that if the volatility increase, then both call and put price will increase. Like that. So in other words, the higher the volatility, the more expensive your options will be for both call and put. Okay, which seems interesting. All right. So call and put are premium on volatility. And so I think, right, someone says when they want to trade volatility, sometimes people just buy call and put in the sense that, right, if you hold call and put option, it's the same, not the same, but it corresponds directly to volatility. So when you want to bet on a company's volatility, in other words, let's say you bet that it's going up, then you just long call or put on that company. If you bet it's going down in terms of volatility, then you just short call and put of that company, okay, option. So that's the interpretation that I'm interested in. Okay, so any question on this? All right. So I think we have time for one calculation. All right. And then we'll go back and do more calculations and talk about the meaning next time. But so I want to do the calculation for delta of a call option. Okay. So again, right, what is the price of a call option? V0 is S0 ND plus minus K e to minus RT ND minus. So it seems very straightforward that if you take the partial with respect to S0, you got ND plus. Is that true? So the answer here is true in answer for some reason. It's a miraculous reason that this is true. It's correct in answer, correct answer, but wrong reasoning. And it's this kind of wrong reasoning that we don't want to sustain, because it will be dangerous if you apply the same, argument for other kinds of derivative. The reason is this, that both d plus and d minus depend on S0, right? Because d plus minus is r plus minus 1/2 sigma square t minus log of k over S0 right here, divided by sigma root t. So in other words, right, if you differentiate, you treat this as a constant and you just cancel them out, that's wrong in terms of calculus, because these guys are also a function of S0. So what you need to do is this. The correct calculation at least must be done like this, right? You must do the product rule on this one. So in other words, it's going to be ND plus S0 differentiate ND plus with respect to S0, and then differentiate this guy, right, with respect to S0, which gives you e to minus RT partial ND minus over partial S0. So what really happens is somehow this is equal to 0. And so you get ND plus as your final answer. But, right, it's not true that you just treat that those other variables as constant and cancel them out. Question? All right. Then the next question is, right, how do you deal with something like this? Okay. Because what is n? What is n to begin with? Right. N is a CDF of a standard normal. Okay. N is a CDF of a standard normal. In other words, it's the integral of the standard normal. Okay, let me do Z. Like that. So if you want to differentiate this guy, you have to go through the chain rule. That is, if you want to differentiate this guy with respect to S0, you must first, right, differentiate this with respect to, sorry, give me a moment here. So yeah, it will be, right, n prime evaluated at the with n prime evaluated at d plus. Yeah, n prime evaluated at d plus times the partial of d plus over partial S0. Oh wait, not n prime evaluated d plus. sorry, give me a moment. Partial of this over that is going to be yeah, I think it's n prime b plus. Yeah, that's right. Okay. So what is n prime? N prime means you differentiate right here, right? You take this function and you differentiate. When you differentiate this by the fundamental theorem of calculus, that becomes f of z, right? The density of the standard normal, d plus, times the partial d plus over partial s0. Is that okay? Okay. So then now you look at d plus right here, okay? And you differentiate with respect to s naught. And so let's carry it out. F of z d plus, right, times partial d plus over partial s naught. So basically, right, this term cancel because it's constant. This is log of s0 over k, right? Differentiate that gives you just 1 over s0 sigma square of t. So here what I claim is partial d plus over partial s naught. For that matter, partial d minus over partial s naught is 1 over s naught sigma square of t. Is that okay? Coming straight from here. Because this term, you can flip it to be log of s0 over k, which is going to be just log of s0 minus log of k. So when you differentiate, right, everything is a constant except this guy, which gives you 1 over s0 times this, which gives you that. Okay. So let's not forget what we're doing. What we're doing, right, is we are comparing this and this, right? And we claim this is 0. In other words, what we're claiming is, right, S0 FZD plus times 1 over S0 sigma over square of t is equal to K e to minus RT, right here. Now differentiate this, right? It also gives you FZD minus times 1 over S0 sigma square of t by exactly the same argument as we did above, right? Apply the chain rule, plug in d minus in this argument, and then do partial derivative. And the partial derivative of d plus d minus with respect to S0 are the same. Okay, so what does that give us? You see this cancel, right? This cancel with this, giving you this interesting expression. Sorry, not this, S0. Okay. And is that true or not? Is that true or not? Okay, is what we need to figure out. Here you see, there's no way for us to eyeball this and say, yeah, it's true, or yeah, it's not true. Why? Because what's fz of x? fz of a little z. It will be 1 over square of 2 pi e to a minus z square over 2. So you see what it takes. What it takes is you must plug the d plus into here. Don't forget what d plus is. D plus is this whole expression. Square it and do your manipulation and then compare with the minus term, and then conclude that they're equal. Okay. Now, this is where I choose not to go that deep into this calculation because it's just tedious algebra. That's nothing enlightening. So in other words, we will accept this. Okay. And not only will we accept it, you will see that this identity right here will come back again and again and again for us in the future. So I will highlight it and I will reuse it, okay, without proof. You can find the proof in the lecture notes. So you can feel free to look at it there, or you can do the verification for yourself. But what I want to say is this, right? When you look at Wikipedia and you just quote something like this, ND plus, do at least be aware of how much calculation goes on behind the scene, right? And even something that we didn't even go into details to give you, right, that single quantity that you're interested in, okay? So of course, I'm not that big on doing tedious calculation, but on the other hand, right, you must appreciate the calculation because supposedly you might have to do some custom, right, calculation with some model that you're not used to before. So without realizing these techniques, okay, you'll be at a loss. Question? All right, so I think this is a good place to stop. Next time, we will continue with the meaning of this term and all the Greek calculations and their meanings. All right, have a good day.